Hello everyone. Today we will start with a new subject. I'll be starting a subject that is discrete mathematics. So in discrete mathematics we will start with sets. The basic concepts like what are subsets, what are equal and unequal sets, what are subsets, what are the ways in which we can specify sets, then what is a universal set, what is an empty set, what are the Venn diagrams, what are the operations that can be performed on set. So in today's session we will be discussing these important topics which are the basics of discrete mathematics. So we will start with sets. What is a set? Now many of us must have studied sets earlier also, but we will assume that we have no knowledge about sets. We will start from the scratch. So what is a set? A set is basically an unordered collection of distinct objects. When I say unordered collection, that means the order does not matter, right? What matters is that there are objects, there are distinct objects in this set, and that's it. So for example, if I have a set named as A, so the distinct elements here are A, B and C. If I have another object B, the distinct elements are 3, 6, 1, 2, 4. So this is a set A having elements A, B and C, and this is a set B having elements 3, 6, 1, 2 and 4. So order, as you can see here, does not matter. Here 3 is coming first, then 6 is coming, then after 1 is coming. So there is no particular order. There is no compulsion that the elements need to be in ascending order or descending order or whatever order. So the basic purpose of having sets is that we can organize objects collectively which are logically related to each other. The basic purpose is to organize them into a group or collect them into a group when they are logically related to each other. So how do we do the grouping in discrete mathematics or in mathematics? That is with the help of sets. So A is a set of 3 distinct elements A, B, C, and B is a set of 5 distinct elements 3, 6, 1, 2, 4. Now one thing that we all must know here is that though there is no compulsion, but the general convention which we all have been following is that this set is always denoted by capital letter. Like you say set A, you say set B, you say set X, and you say set Y, right? And the elements of the set are always in small letters. Like here you can see small a, small b, small c. So this is the general convention which we have been following, that the names of the sets are always in capital letters and the elements of the sets are always in small letters. So what are the elements of set A? Small a is an element of set A, small b is an element of set A, small c is an element of set A. When I separate them with commas, they become distinct objects or distinct elements. So if I write ABC like this, then these are not distinct elements, then ABC is one element of the set. But when I separate them with commas, that is A, B, C, then they become 3 distinct elements or 3 distinct members of the set. So always when you want to write distinct objects, they must be separated by commas like this, and all the elements of these sets are enclosed within these parentheses. These are known as the parentheses, which here are the curly braces. Okay, so these are the parentheses. All the elements or all the distinct elements of the sets are separated by commas and enclosed within parentheses. So this is how you specify sets, or this is what a set is. Now when A is now you can see that in set A there are 3 elements or members. Now these are the elements or members. You can call them the elements, you can call them the members, whatever you feel like calling them. They can be called members or elements of the set. So here you can see that in case of set A, there are 3 elements. These 3 elements are A, B, C. So if A is an element of A, if small a is an element of capital A, then I can say that A belongs to set A. So this is how I write: A belongs to A. This is the symbol of belongs to. So I say that set A belongs to capital A. Similarly, I can say B belongs to set A. Yes, B belongs to set A because B is a member of set A. Similarly, I can say that C belongs to set A. Yes, C belongs to set A, obviously, because C is a member of set A. So this is how you denote the symbol of belongs to. Whenever a member belongs to a particular set, you write A belongs to set A, B belongs to set A, C belongs to set A, like this. Now if I take one member called P, so does it belong to set A? Can you see P anywhere here in set A? No, you cannot see it in set A. So that means if it is not present in set A, it does not belong to set A. So how will you denote that? With the sign of negation. That means P negates A. This means P does not belong to set A. So when it belongs, you write like this: A belongs to A, and when it does not belong, you write P does not belong to set A. Okay, now let us take one more set here, C, which is equals to B, C, A. Now we will talk of equal and unequal sets. For two sets to be equal, they need to meet two criteria. The first criteria is the number of elements in both sets. So, first of all, the number of elements in both the sets should be same. Say for example, I am taking two sets A and C. So, you can see here the number of elements in A are 1, 2 and 3, right? There are 3 elements in set A. Similarly, the number of elements in set C are 1, 2, 3. So, again there are 3 elements in set C. So, that means number of elements are matching, the number of elements are same. Hence, they are meeting the first criteria. Now, let's move on to the second criteria, which says that elements must have similar values. So, the elements of both the sets must have similar values further to be called as equal sets. So, here you can say the 3 elements are A, B and C. In set C also you can see the 3 elements are B, C, A or A, B, C. So, that means the values of the elements are also same. Now, here you may say that it is in the order A, B, C and here it is in the order B, C, A. But as I told you in the beginning itself that the order has no relevance in case of sets. Why? Because sets are called unordered collection of distinct objects. So the order does not matter. What matters is the value of the elements or members. So here also we have BCA, here also we have BCA. So both the criteria are being satisfied. The first criteria, number of elements are same. There are 3 elements in set A. Again there are 3 elements in set C. So the first criteria is being satisfied. Then the second criteria is also being satisfied since the values of the members in both the sets is same, ABC, BCA. Alright, so I can say that set A is equal to set C. So both these sets are equal. Now moving on, if we take set B and set C. So first criteria, first we will consider number of elements in B, 1, 2, 3, 4, 5. 5 elements in set B. Number of elements in C, 1, 2, 3. 3 elements in set C. So, are the number of elements in both the sets equal? No. They are not satisfying the first criteria itself. So, in that case, B is not equals to C. So, that means B and C are unequal sets or B and C are not sets are not equal. Now, if I take another example of a set D. So, in set D, say for example, I have 5 elements again, 3, 6, 1, 8 and 9. So, again we will see if D and B are equal or unequal. Now here B also has 5 elements and D also has 5 elements. So first criteria, they are satisfying. Then moving on to the second criteria, what does it say? The value of elements must be same, no matter in what order they are, but their values must be same. So are the values same here? 3 here, 3 here, 6 here, 6 here, 1 here, 1 here, 2 here, 8 here. Now these values are not matching. 4 here, 9 here, these values are also not matching. That means since the values of all the elements in set B is not matching with all the elements of set D, that means set B is not equal to set D. So this is the concept of equal and unequal sets. Okay, now we will see how we can specify sets. Now one way of specifying sets is what I told you, like you list out the members of sets A, B, C. So we listed out all the members of the set, and hence we said that set A is equals to a set of 3 elements A, B and C. So there is one more way by which you can specify the sets. We will see from the starting. Okay. Now before I tell you the two different methods of specifying sets, you must know that until and unless all the members of a set has been listed out, you cannot say that a set has been determined. Say for example, I take the same example, set A equals to A, B, C. Now set A is having 3 elements A, B and C. But if I only specify these 2 elements and do not mention about the third element, I do not say that set A is specified. It is not specified or it is not determined. So a set is not determined or a set is not specified until and unless all the members of the set has been listed out. Now this particular principle, that we cannot say that a set is determined or you cannot say that a set is specified unless all its members have been listed out, is known as the principle of extension. This particular mechanism is known as the principle of extension. Alright, now moving ahead, the two different ways of specifying sets. The first way of specifying sets is by listing the members. Alright, so the first way of specifying your set is that you list out all the members of that set. Say for example, I have a set A which is a set of vowels A, E, I, O, U. This is a set of vowels. So A, E, I, O, U are its members. So I have specified set A by listing out all its members. I listed out A separated by a comma, then E, then I, then O and U. So this is one mechanism of specifying the set. Another mechanism of specifying the set is by stating the property, of members of the set. Now instead of listing out the members individually here, what I will do, I will specify the properties of the member of that set. For example, there is a set B. I say B is a set of X such that X is even integer and X is greater than 0. So here you can clearly see that I have not listed out the members of this set, but what have I done? I have stated the property of the members of this set. Now let me tell you how you read out this statement. This is read as B is a set of X. B is a set of X. Now X here is representing all the members of the set B. So B is a set of X. Then this colon represents such as. This colon is known as such that X is even integer. So the moment you read that B is a set of X such that X is an even integer, so what numbers come to your mind? Numbers like 2, 4, 6. Further it says and. Now this comma is read as and. Whenever there is a comma, it means and. So a colon means such that and a comma means and. and x is greater than 0. Now when I say x is greater than 0, what does that mean? That means all the values of x are positive, because in the number line all the numbers greater than 0 are positive numbers. So when I say x is an even integer and x is greater than 0, that means I am talking of positive even integers. So that means B is a set of numbers like 2, 4, 6, 8 and so on. Why so on? Because there is no limit to even positive integers. They will keep on going till infinity. Hence I left it like this, after comma, so on. So these are the two methods of specifying sets. Now here you saw that there was no limit to the number of elements. Hence a better approach here is to specify the set in terms of the property of its members. And in cases where you can specify or list out the members easily, like there were just 5 elements in this set, so the better approach is to list out the members themselves. That is how you can specify the set. So in most of the cases, what approach we follow is that when the number of elements are less and they can be easily listed out, you specify a set by listing out the members. When the numbers of elements are more, say 15, 20, which is very difficult to specify individually, you cannot keep writing A, E, I, O, U, B, C, D till 15 alphabet letters or 20 letters. So in that case, or in case where there are infinite number of elements, like here you saw that positive even integers are infinite, right? So in such cases, the better approach is to specify a set by stating the property of the members of the set. So these are the two ways by which you can specify the property, specify the sets. Now this method or this mechanism that you can specify a set by stating the property of its members is known as principle of abstraction. This principle is known as the principle of abstraction. That is the very thing that you can specify a set by stating the properties of the members of that set is known as the principle of abstraction. Now, let us look at subsets. What is the concept of a subset? I have a set A which is equal to or which has elements 1, 2, 3, 4, 5, 6 and 7, right? Then I have another set which has elements 1, 2, 3 and 4. Now here you can see all the elements of set A, are they present in set B? No. Some of the elements of A are present in set B, but all the elements of set A are not present in set B. But in case of set B, you can see that all the elements of set A are present. In case of set B, you can see that all the elements of set B are present in set A. Yes, we can clearly see that these elements of set B are present in set A. And these are all the elements of set B. So therefore we can say all the elements of set B are present in set A. In such a situation we say that B is a subset of A. Now this is how you denote subset. B here is a subset of A, or you can also write here it like this, right? So B is a subset of A. Now there is one more condition over here. Now let us assume that there is one more set having members 1, 2, 3, 4, 5, 6 and 7. Now here also you can see all the elements of set C are present in set A. Yes, set C has elements 1, 2, 3, 4, 5, 6, 7. So all these elements are present in set A. So I can say that set C is a subset of set A. Yes or no? I can say that. But at the same time you can see that set A and C are equal. Set A and C are equal? Yes or no? Because they have the same number of elements plus the values of all their elements are same. So hence I can say that A equals to C. But when I talk of A and B, B is a subset of A. B is a subset of A, but B is not equal to A. So in cases where one set is a subset of another set, like here C is a subset of A, but C is also equal to A. So here I just call it a subset. But in cases where like B is a subset of A, but B is not equal to A, in this case I call that B is a proper subset of A. So the notation for proper subset is like this. B is a proper subset of A, or like this. So this is the difference between a subset and a proper subset. Now we will discuss universal set and empty set. So first of all we will discuss what is a universal set. Now any set under investigation or any set under consideration belongs to some or the other universal set in most of the cases. Like here if I talk of this set A of vowels, A, E, I, O, U. So it belongs to the family of alphabets. Yes. So that means the universal set for this set is, for this set A is the alphabets, the set of alphabets. So any set that you consider, say for example if I am studying a set of complex numbers, so that set belongs to the universal set of the number system. So any set that we are studying belongs to, in most of the cases, belongs to some universal set. So this is the concept of universal set. Now if I talk of an empty set, empty set is, as it is clear from the name itself, if B is an empty set, that means it has no elements and is denoted by a phi symbol. So empty set is one set which does not have any elements. Now if I take an example, I say B is a set of X such that X is a positive integer, such that X is a positive integer and X square is equals to 3. So what am I saying? B is a set of X such that X is a positive integer and the square of X gives you 3. Now any positive integer 1, 2, 3, the square of these integers will never give you 3. So this is a condition which cannot be satisfied. So what would be the elements of B in that case? No elements, because no such positive integer satisfies this condition that X square equals to 3. So in this case B is an empty set. Now there are some notations which are universally used in mathematics, right? Unless you yourself specify that this is the notation that you will be using. So by default the notations that are being used in discrete mathematics or mathematics are: N denotes, capital N denotes natural numbers, Z denotes integers. Now when I say integers, it could be any integers, positive and negative both. Q denotes rational numbers. Then R denotes real numbers. C denotes complex numbers. So these are the notations that we will be using throughout in discrete mathematics. So you must know these notations in advance, because throughout, all through, wherever you study discrete mathematics, these notations are used for natural numbers, integers, rational numbers, real numbers and complex numbers. Okay, now we move on to Venn diagrams. Now the Venn diagrams are a pictorial representation of sets, or in other words, when I graphically represent a set, that is known as a Venn diagram. Now it is represented in a plane region, in a plane wherein this rectangular region represents the universal set, which is denoted by capital U, and the circular discs represent the set under consideration. So here this disc is representing one set called set A, and U represents the universal set to which this set A belongs. So this is a Venn diagram. We will see some examples. Say for example, if I want to say that A is a subset of B, so how will I say that? Using a Venn diagram. Here you have the universal set, then you have a disk B, and within which you have a disk A. Now I said A is a subset of B. That means all the elements of A are contained in set B. Or in other words, I can say A is contained in B or B contains A. So this is what we have done here. A is contained in B. So this is a Venn diagram of A is a subset of B. Similarly, if I have two disjoint sets A and B. Disjoint sets means those two sets which have nothing in common. So if there are two disjoint sets A and B, so they will be represented like A and B lying separately within the plane. This is one set A and this is one set B. So this represents that A and B are disjoint sets, right? So this is a Venn diagram for disjoint sets. Similarly, I take two more sets like this. Like this, I take two more sets. Within the universal set, I have a set A, I have a set B, and both of them are overlapping. Now this overlapped region represents that both of them have some elements in common. So that means A and B have some elements in common. Then this region represents all those elements which are just present in A and not in B. Similarly, this region represents all those elements which are just present in B and not in A. So this is the concept of Venn diagrams. Now we will discuss the complement of a set. Complement of a set. So as I told you, all the sets or any set under consideration belongs to some universal set. So if I am talking of set A, right, and set A has elements 1, 2, 3 and 4, right? So you can clearly see that set A is a set of natural numbers. So in that case, if I say complement of A, which is represented like this, so complement of A would be all those elements which are not present in A but present in its universal set. So it will start from 5, 6, 7 and 8 and so on, because natural numbers go on till infinity. So this will be the complement of set A. Now I can say that means the complement of this set is the universal set minus that particular set. Now the relative complement we will see. The relative complement of a set is taken of one set in respect to another. Say for example, I have two sets. Set 1 has elements 1, 2, 3, 4, 5, and set B has elements 1 and 2. So I say the relative complement of set B with respect to set A, and this is denoted like this, A for backward slash B. This is how you denote the relative complement. So this reads the relative complement of B with respect to A. So how do you find out the relative complement? So if I want to find out the relative complement of B with respect to A, that means the resultant set will contain all those elements which are present in set A but which are not present in set B. So what are the elements that are common to set A and B? 1, 2. That means the resultant set will have all the elements excluding 1 and 2. That is 3, 4, 5. Hence you can say that the relative complement of B with respect to A is equals to A minus B. So this is the concept of relative complement. Now moving on, the operations on set. Operations on sets. There are two basic operations that can be performed on sets. Those two operations are union and intersection. So first of all, we will discuss union. So the union of two sets A and B, if A contains elements 1, 2, 3, 4, 5 and B contains elements 4, 5, 6, 7, 8. So the union of A and B, so this set, resultant set which we will obtain after the union of A and B will be a set which will contain all the elements which are present in A and all the elements which are present in B. So what are the elements of A? 1 it will be copied, 2 will be copied. Now 3, 4, 5 here you can, 3 and 4, 3 will be copied. Now 4 and 5 here you can see are common to both the sets. Since they are common, even they will be copied. But they will not be repeated twice. They will be written just once. So if 4 and 5 is present in A and 4 and 5 is present in B also, that does not mean you will write 4 and 5 twice. You will write it just once. So 4, 5, then elements of B which are 6, 7, 8. So this is the set after the union of two sets A and B. So hence if I state in terms of property, A union B is a set of X such that X belongs to A or X belongs to B. Here OR is in sense of OR and. Why? Because X contains all those elements which belong to A, X contains all those elements which belong to B. If at all there are common elements, then I can say AND here. But if there are no common elements, then I will say OR. In terms of Venn diagrams, how will you represent A union B? A union B will be like this. Now how will you shade A union B? This entire region represents, shaded area represents A union B because it includes the common elements, it includes all the elements present in A, it includes all the elements present in B also. Now next basic operation on sets is, or the next operation on sets is intersection. Now when I say the intersection of two sets, the intersection of two sets, like again I will take this same example, 1, 2, 3, 4, 5, 6 and set B contains elements 3 and 4. So the intersection of these two sets, that the resultant set will contain all those elements which are just common to both, not the distinct elements. Now here there are two elements which are common to both or which are present in both sets. These are 3, 4. So the resultant set will contain only these two elements. That is if I want to state the set A intersection B in terms of its property, I will say A intersection B is a set of X such that X belongs to A and X belongs to B. So that means X is a common element of A and B. In terms of Venn diagram, if I want to state it, how will I state it? Like this. I have a universal set, I have two sets A and B. So since A intersection B is a set of common elements of A and B, so only this region will be shaded. So this shaded region represents all those elements which are common to A and B. Hence this Venn diagram represents A intersection B.